You, Hank.
Yeah. Hey, thank you. So we're going to start with the Computational Design Conference in 2020. I'm going to make my welcome to country. I would like to begin to acknowledge the traditional custodians of the land we meet today, the Gadigal people of the Eora Nation, and pay my respect to the elders past and present. I extend this respect to the Aboriginal and Torres Strait Islander people here today. So thank you, students, for joining us. Thank you for joining us online, wherever you are. It's a bit an odd year this year. We probably all suffered from that quite greatly. So I'm deeply thankful for the students' work you've done this year. I think you had the hardest graduation year ever, the hardest study year probably ever, with the whole kind of changes. I think there's never really an event, at least in my lifetime, that interrupted that much of what we want to do. So thank you for all the hard work you've done there. Let's keep the conference going. We've got 2 rooms today. We've got 2 different presentation slots in order to get through the day quite quick and smoothly. So half of the group will be down here with Nicole and Daniel as the reviewer. The other group will be upstairs with me as the reviewer. And then we're just going to keep going through the day. If you want to see the schedule, it's on unswcode.org, conferences 2020. So you can see when you are, where you are. Again, both sessions will be recorded and will be on Teams. So very likely your industry partners will join via Teams. And we invited them to come physically here as well. But as you know, there are restrictions of how many people can be in a room. And with the COVID crisis at the moment, a lot of the industry partners are quite busy with their work, so they couldn't really spend a day off because they've been working day and night to finish their deadlines and making sure they can keep their jobs. All right, I'm going to hand over to Nicole, who will introduce our keynote speaker today, Brady Peters. Brady, thanks a lot again for being our keynote speaker. It's a great honor to have you, and Nicole will introduce you.
I have to put the camera down because I'm so short. Welcome again, everyone. I'm just going to quickly introduce Brady. So Brady's a Canadian designer and researcher, and he's currently an assistant professor, right, isn't it, Brady? You can just nod, yep. At the University of Toronto. He specialises in architectural acoustics, environmental simulation, computational design, and digital fabrication. In his professional life, he was an associate partner at Foster's and Partners, and a key member of the specialist modelling group, where he was involved in projects using complex geometry and environmental simulation. He's also a director of Smart Geometry, which is an organisation that promotes the use of computation in architecture. And he's highly published, and one of the most recent publications is Computing the Environment, which is available in the UNSW library. Digital design tools for simulation and visualization of sustainable architecture. And I'm really happy that Brady's been able to join us here today. It is Thursday where he is, and it is Friday here, which is always a bit odd. So there's a fair time difference, and we've been able to accommodate that here today. But I guess I should explain why I chose Brady to come and give a keynote today. You guys, the graduating class of 2020, had me as course convener in T2 for digital collaboration. I asked you to develop workflows that would pull together all of the phenomena in the environment and one, I guess, optimization and analysis software that you guys hadn't used yet was Pachyderm. So you gave that a red hot go and you loved it, right? So anyway, we waded into architectural computational acoustics. You guys read some of Brady's work at the time, and also I should say last year's keynote speaker, Jane Burry, has worked quite a lot with Brady as well. So there's lots of connections and small degrees of separation. So one of the reasons I asked him to come today was because we had engaged with architectural computational acoustics in T2, and I felt it would be really interesting to see where that's going. And also I think Brady's obviously a leader in computational design space. So I'm really interested to hear your thoughts on where to next for computational design and digital tools in architecture. So I will hand it over to Brady now. without delay, we're going to turn you around so you can see the audience. And thanks again.
Okay. Well, thank you to Nicole and Hank for the invite to come and speak to you guys to give this keynote. So it is, like Nicole said, it is Thursday here in Canada, where I'm presenting from. And I think if you guys can hear me, I don't know, I can't really see you guys so much, but yeah, okay. Then I'm going to, I'm going to give a PowerPoint. And so unfortunately you won't be able to see me, but we can have a discussion afterwards, and hopefully, you know, answer any questions that you might have. So let's see if I can make this work. Okay. So the title of the talk that I'm going to give today is Sound and Surface. And this title actually comes from an exhibit that I gave at the gallery at the architecture school in Toronto, which was sort of like last fall to early last year. And this exhibit was a really valuable experience for me as a way to sort of recollect all of the many acoustic experiments that I've done basically over the last 10 years. And I think one of the main findings, I would say, of the work is that we can really think of architecture as an instrument, right? And through the manipulation of geometry and surface material, we as architects can create sort of spatial sonic effects and create this acoustic experience within buildings, right? So this is where I work. This is the new Daniels faculty in Toronto. We're on an island in the middle of a city. This is one of my labs that I run. So this is the robotic prototyping laboratory. We have other digital fabrication equipment too, but this equipment is specifically mine to operate for my research and for my graduate students. I also run an acoustic lab, so we have various acoustic measurement equipment, as well as this sort of emergent spatial oralization lab that I'm also developing, which is working, but we're still sort of fine-tuning. And the work that I do sort of, I think, encompasses these realms, right? So there's digital fabrication and computation, and design practice, but also architectural acoustics and where we find these four areas meeting. But what I'd like to do in this talk is sort of go back to see where I've come from, to sort of like map this trajectory through my career. And I often find, you know, students are interested in sort of these professional trajectories that people take. So I graduated with my architecture degree back in 2001 with my professional master's in architecture from Canada. And I was really intrigued by the architecture that was happening in Europe, and so decided to move to London, UK. And you can see the Foster 30 St. Mary's Axe office tower here right in the foreground of downtown London. And this was just going up actually during the first years that I was living in London. And it was a really important pivotal project for me to see this building being realized in this amazing city. Now, when I arrived in London, actually my airplane ticket was actually for September 11th, 2001, which was really not a very good time to travel or to fly. Number one, obviously, you know, all the flights were canceled and it took weeks just to get to London. But also professionally, like a lot of the job offers that, or job prospects that I had dried up. I was fortunate, though, that one of those prospects did not. and that was to work at Bear Happold. So I got a job out of architecture school in an engineering practice. And so I worked in the London office in the structures group 054 structures with Mike Cook for this firm. Now Bear Happold is, which you may or may not know, but Bear Happold is a now anyways a very large engineering practice that spans many different countries, but sort of grew out of a research and design trajectory that was established by its founder, Ted Happold, when he took up the post of being the head of the Joint Architecture and Engineering College at the University of Bath. And so many of the early projects really were interested in like this efficiency of materials and sustainable building and innovative building practices and design practices, and did a lot of work with Frey Otto, like you see here. And like I said, I was working in the London office, and I was actually the physical model maker. So coming out of my architecture degree, I did not use computers really very much, except to check my email, do a little bit of 2D CAD, but we did do a lot of physical model making. So I got a job building physical models at Bear Happold. These are a selection of some of the models that I did. In the process of doing these models, I also did a lot of hand drawing, and also hand drawing in the to help the engineers communicate their ideas, whether they're design ideas or performance ideas about buildings. And as I worked at Bear Happold, I began to use the computer more and more. And at first, using the computer was in the service of making better physical models, but ultimately I found that I could just sort of move fully into the digital realm and away from actually building physical models. This is a project that I worked on when I was at Bear Happold. This was a house, actually, by the architecture practice Yoshida Findlay. And the digital model that you see is what we got from the architects. And we, as the structural engineers, were hired to make that stand up. As you can see, it's sort of floating on the ground. So we needed to reconceptualize the form of this somewhat in order to, make it a structurally sound proposition. And so what I did was sort of take this radial pattern and create these structural ribs and then photocopy them. And it looks sort of like a laser cut model, but this was actually done all by hand. And I think that's the critical thing here, is that this sort of predates much digital fabrication and also, computational design and parametric design. And so any sort of change that was made to the designs was like really onerous. And so I really was thinking, like, is there a better way, right? Like every change took days and days and days. In fact, it took weeks to build this model. Is there a better way for us to be designing? And I happened to find actually maybe it was like the next month or something, I went to this conference at the University of Bath, which was the very first ever Smart Geometry conference. And I saw this lecture by Hugh Whitehead. Hugh Whitehead was a leader of the research group at Foster & Partners. And he was showing some parametric design software that he had used to design the 30 St. Mary's Axe office tower in London that I had seen being built, right? And this Hugh's lecture really was very inspiring to me. I was like, this is the answer I needed, right? This is the answer I was looking for. So what Hugh could do with this parametric design software was like not only like control the form, but then also like link the sort of two-dimensional section to the three-dimensional plan profiles, and then also be able to iterate the parametric engine in order to produce the many different iterations of the plan profile. So this software that we were using is all done in MicroStation using a industrial design sort of plugin for MicroStation called Dimension-Driven Design. And then Francis Aish, who was working with the team, wrote these wrote this sort of pieces of software that would then be able to automate the control of this parametric software. So you can see here, this automation is basically producing the plans of the Swiss Re. And this is sort of the level of parametric design at the time, right? I saw Hugh give this lecture and I was just like, wow, this is great. I have to join this practice. And so I was fortunate enough to apply to Foster & Partners, and somehow through my connections at Beer Happold, actually be able to land a job working with Hugh Whitehead and Francis Aish in the specialist modeling group at Foster & Partners. And so that's where I spent the next 6 years of my life, working with Hugh and Francis on these like crazy awesome projects with these crazy awesome people. The buildings that you see here, this is what Hugh liked to call the 6 seminal projects of the group. These projects were like largely all done by the time I arrived. So I've got another 6 seminal projects that will be my 6 seminal projects, but we'll get to those in a bit. So the first project that I worked on, and I was basically thrown right into it, was the West Kowloon Master Plan, and specifically the Great Canopy for this master plan. So one of the, I guess, things that we did as part of this research group was sort of translate architectural design intent into realizable built form. And so you can see like Norman Foster's sketch here for the sort of grand roofscape, and then the digital model that was then developed out of, you know, translating the sketch, working with the designers, and then translating that into this digital model. So this roof, however, was part of like this much larger master plan for the Kowloon area that included museums and stadiums and residential and this whole retail center and public transportation, et cetera. And this roof surface was like part of this environmental narrative that the team was developing, this environmental performance narrative. You can see Narinder's sketch here that sort of explains sort of how this roof would become this environmental modifier to make the outdoor environment or the semi-outdoor environment a very pleasurable place to hang out and inhabit the spaces that it would create. And so again, this project, I used these tools that Hugh and Francis were developing using dimension-driven design. So you can see here these profiles that we're creating along these guide curves. This is the sectional profiles that we've defined and we're then modifying and then copying into place. And the original intentions for this roof surface were to use these undulations as a way to give structural rigidity to the structure, and which is a fine idea, and this sort of works structurally. You can see the undulations here. However, something that we didn't really take into account, like at the time, is like just the scale of this roof, right? So this roof surface is actually about 1.5 kilometers long, and undulations at that scale really aren't doing what we needed them to do. So we needed to develop structure at a much finer resolution. And so we started looking at space frame geometries, working with the engineers Arup to do this. And we realized that the number of elements that we were going to have to draw was massive, right? Just massive. And these parametric tools, like that I just showed you, dimension-driven design, while they were good for like defining the guide curves for the Swiss Re office tower or for the form of this structure, they simply didn't scale up to generating this complexity, like these 200,000 elements, a minimum that we would need for the space frame. So how are we going to do it? And this is where I found scripting, like computer programming. And so this was like this was another epiphany for me, a major moment in my professional career where I was like, wow, okay, this is the answer. And so I worked with Francis Aish, who's an engineer working with the team, and he basically showed me how to write scripts in BASIC, this programming language that was in MicroStation V7. And so I programmed the first space frames for Kowloon in V7. and they took forever to generate, right? Like it took almost 24 hours to generate one whole option of the space frame, which is actually great because I mean it would have taken like whatever 24 months to do if you were doing it by hand, and you would have had a lot of errors. And this was sort of error-free, and it only took a day. However, like just a couple of weeks into this project, the new version of MicroStation came out. It had this VBA programming environment, which was like infinitely quicker. And the generation time for this space frame sort of went from 24 hours down to like 10 seconds. And that was just like another, major moment where we realized just like the power of this, the potential of computer programming in the design environment. So, which is great from a numbers perspective. But when we look back at this project, another lesson that we learned about the use of computational tools was also that the parametric model really became this place where a lot of different disciplines could join. And it was like this synthesis of the design that combined, ideas about structural engineering and the environment and the integration with the landscaping. And so a lot of different disciplines, the parametric model really brought together a lot of different disciplines. And we thought this was really quite notable as well. One of the criteria for this project was to actually build a very large physical model. And prior to, digital fabrication, we were thinking, wow, this is really wonderful. We've been able to generate this, but we can't build it. We can't build it unless we can actually we thought it was like crazy, but like script robots to build this structure. We thought this was totally science fiction. How are we going to do it? Then we found 3D printing, and so we're like, okay, this is great. So we can generate the design, we can then chuck it to the 3D printer, and we can build it. And this was so wonderful. We convinced the firm to actually purchase a 3D printer. This was apparently one of the first 3D printers in a UK architecture office. I think Morphosis had 3D printers for a couple of years already, but anyway, this was pretty exciting. And so the next project that I worked on, which was this large form found tent, I was able to use 3D printing actually within the design process. So this project here, again, I was using the computational tools, developing computer scripts. And here we were looking at, because we're looking at these very special structural forms of these cable nets, I borrowed an algorithm from Dr. Chris Williams at the University of Bath and basically programmed this into MicroStation to create this software that would create these form-found net structures. This was before Grasshopper and Kangaroo, obviously, which sort of is a very similar type of program. Anyways, so we could generate these computationally, but then we could also instantly 3D print them. And so what we could do is sort of generate multiple options per day, me working with the project design team and developing all of these different tent options. And this was a really powerful thing for the office, but also for me personally, sort of having come from a physical model making background. It was this, like Hugh Whitehead says here, this use of rapid prototyping, which closed this loop in this digital design process because of the design decisions that are made by physical models. And this is, I think true, very much true at the Foster & Partners office. This is a project of that, or a picture of that project as it is completed. When I was at Foster's, I had the great fortune of working on many projects that did end up being completed. So this is another project I worked on here. This is the atrium space for a large school project in Peterborough. This is the Willis Tower in London, just down the road from 30 St. Mary's Axe. This is a large stadium in Glasgow, another space frame. And finally, this is Canary Wharf retail and underground station. And this is the Copenhagen Elephant House. But I want to just talk about this other project here briefly before we jump into some of the acoustic stuff. So this is the Kogod Courtyard done at the Smithsonian, and this was one of the more major projects that I worked on while I was at Foster's. This is Norman's sketch here, which shows this, what he liked to think of as this very lightweight structure that would sort of float gently down and rest on the existing building and cover the existing courtyard and create this new space for the city. And this was our digital model that was sort of that translation of Norman's idea. Ultimately, it's a very simple project. You know, it's an existing courtyard space, so we were, you know, responsible for basically creating this large roof structure. The landscaping was done by another practice as well. And there was many different constraints on the design project, right? So there's a very historic building, and so there was like a lot of heritage restraints. There was another series of renovation projects ongoing in the building at the time, which the Foster and Partners office was not doing, and so we had to integrate with them. And there's a lot of like sight lines and city planning issues as well. So the project was relatively constrained going into it. And so we used parametric design again as a way to investigate the design space, the formal design space for the project. And, you know, this animation here is showing like some of the many different formal options that you could easily produce, you know, once you have a parametric design system built. And I think what was interesting, or what I found interesting working in practice on parametric design, is that even though you have this potential, by the time that this parametric design model is built, the form is actually pretty much set, right? And so you don't actually get to like utilize the power of this parametric design model. However, where the real power is that we found was not so much in the sort of formal variation that you could produce, but the different types of data that could come out of the parametric model. And so we were able to produce like what we called all these different representations of the project. So we're producing, you know, models for structural analysis, models for fabrication, models for acoustic analysis, models for rendering, models for drawing extraction, models for lighting analysis, et cetera, et cetera. So this was like a really, again, like a very important part of the design process that brought a lot of different ideas together. The panelization strategy, again, that was like an interesting geometric exercise. You can see the analysis image on the left showing the amount of twist in the different panels. So the panel layout was set by the construction grid, and there was a design aspiration to have this in a diagonal. And so we were not able to get flat panels if they were all to meet on their edges. So I came up with this algorithm to flatten these panels. So this is what these panels look like from the top. But one of the reasons to talk about this is that this was one of the first projects I worked on that integrated sound into the design. And so the project came about because the client was very intrigued or very taken by the courtyard at the British Museum. And the courtyard at the British Museum, again, another lovely project done by Foster and Partners with Bear Happold, but that was completed before I joined either practice. The courtyard at the British Museum is a very reverberant space, probably similar reverberation time to a cathedral or something. And that's just the particular character of that space. However, for this space, the client demanded a space that could be used for lectures or performances, musical performances, or gatherings with many people where they could have wine and cheese and so forth. And so there was a need to bring that reverberation time down. So not to have the reverberation time of a cathedral, but to have a reverberation time more in the range of like a lecture hall or something. So given that this space is what it is, without any sort of acoustic treatment, the reverb time would be about 8 to 10 seconds, which is very long and about the time of a cathedral or something. So we needed to find a way to bring that reverb time down. Now, one of the challenges for this project is the material palette is very limited. So you have these heritage restrictions on the walls. So the walls are stone and must remain stone. The floor is going to be stone as well. Can't carpet the floor. And which sort of basically leaves this steel and glass roof structure. And steel and glass themselves are not very acoustically absorbent. So this was the challenge, was sort of where do we find a place to put the acoustic absorber? And the answer that we came up with was to actually put that in the structure. And so you can see here the section through the beam, and we basically were able to tune the absorption, tune the acoustic characteristics of the space through actually changing the depth of the beams. So the depth of the beams could be tuned as much for structure as for acoustics. And so you can see here our mock-up that was done, and we had that tested in the acoustic lab to figure out what absorption coefficients were. We could then sort of take that knowledge and build that back into our computational model to figure out actually what the acoustic performance is and what it needed to be if we changed the beam depth and so forth. So this is the project as it is built, and what we sort of, it sounds great, by the way. I don't know if it's ever been tested, but having gone there, it's like really quite a nice acoustic characteristic within the space. Juhani Plasma, in his book Eyes of the Skin, writes that every building or space has its characteristic sound of intimacy or monumentality, invitation or rejection, hospitality or hostility. A space is understood and appreciated through its echo as much as its visual shape. And I think what's important here is that not just that sound has the powers to be intimate or monumental or to be hostile or hospitable, but that also that sound is inevitable, right? And that all buildings have sound. And so this was like a really important realization as well. As, you know, like many buildings, perhaps we don't think about sound, but no matter if we think about it or don't think about it, that sound is going to be inevitable. So what is it, Foster? I was decided to leave the practice to pursue a PhD. And so in 2008, I left the practice right before the economic crash. I think I was one of the last people to actually quit a job in London and joined the Center for Information Technology and Architecture in Copenhagen, Denmark, at the Royal Danish Academy of Fine Arts. And there I was working with practice on this problem of acoustics. And so basically what I had seen over like the last 10 years of architectural practice was like this huge, and taken part in, right, was this huge increase in design technology, but also this introduction of digital fabrication into the world. And so combining these, we see this like Branko says here, like over the past decade, we have seen architecture, the reemergence of complexly shaped forms and intricately articulated surfaces, enclosures and structures whose design and production were fundamentally enabled by the capacity of digital technologies to accurately represent and precisely fabricate artifacts of almost any complexity. And so my question was, basically going to my PhD, was can these surfaces be performance driven? Can they sound good? So one of my first sort of attempts to understand or come to terms with this question was to basically take these equations from acoustic science and create, you know, some sort of architectural generating scripts from them, right? So here we see one example of that. This is taking the formula for a Helmholtz resonator and thinking about this instead of as like this more singular absorber at a singular frequency, but turning this into a broadband absorber through this multiplication of many different resonators. And so this is like one of these examples, and I wrote many of these different scripts and I did many of these different surfaces, which was like wonderful, and they look amazing and so forth. But problem is I didn't really know how they would sound like, right? I didn't really know if they would actually work if we built them. I mean, the math was there, and we could certainly generate them, but what would they sound like? I didn't have the digital tools to be able to predict that. And so my quest then became to sort of like improve digital tools to integrate sound into the, the digital design environment, but then also to fabricate and to verify through experience, like through measurement and experience, what these surfaces might sound like. And so I built, many of these structures through my PhD research. This one was done at Smart Geometry. This one was done as part of a design studio that I taught with Martin Temke. Another research project that followed on from that first one. I also collaborated with a Danish architecture practice, JJW, to consult on this large school project that had many different interesting acoustic requirements. And what I wanted to talk about today, actually, in talking with Nicole, she talked about some of the experiences that you may have had in designing projects for acoustic performance. And so this project was done while I was taking courses as part of my PhD program. So I was taking courses at the Danish Technical University in their really excellent acoustics program. And so as part of that program, in part of the architectural acoustics course, we actually collaborated with some architects, some architecture students, to come up with a design. And this is the project. So there were 6 of us, six engineers and 3 engineers and 3 architects to do this project. And so this is the site here. You can see it on the very top. This is like this design for this pavilion. And the architects had all these interesting ideas about this like faceted landscape. And so meeting with them, one of the first steps is to talk about like these conceptual ideas about architectural design and acoustic performance. So we can sort of use these sketches as a way to like trace rays and how sound might bounce around the space or be enclosed by the space or not be enclosed by the space, what different materials might be. You can see at the bottom here, we already were starting to identify like reflectors, diffusers, and absorbers. One of the main driving concepts for the pavilion would be these walls in the landscape out of concrete or wood and steel with these 2 different spaces, right? So there'd be like this lounge area and this performance area, and then it would be covered by this like triangulated roof structure. And so in architectural practice, I mean, people are producing 3D models all the time now. This is not very uncommon. However, what is potentially more uncommon is actually producing models that are actually suitable for simulation. And so the models that we were getting from the designers were like completely unsuitable for simulation. And so one of the first steps is like to develop this like appropriate, this performance appropriate design model. So i.e. watertight with controlled triangulation and having these layer separated materials. The second thing to do is just to understand where you want to go with this, right? Like, what are your performance goals? So if you can do simulation, what do those simulations mean in terms of actually meeting or not meeting some sort of criteria? And then you get around to actually doing these simulations. So this was one of the first simulations we did to determine whether we wanted to actually have this as an enclosed space or not. And if we look at our analysis here, we can sort of see the color diagrams are showing loudness of the seating space. And on the bottom, we see reverberation time. So for those of you who don't know, reverberation is the time it takes for sound to decay to inaudibility in a space. So if one claps their hands, the reverb time is the time it takes for that sound to, all those echoes to subside until you don't hear them anymore. And our goal for this space was to have a reverb time of about approximately 1 second. And we could see that if we were having this open space, you see on the left, it was impossible to get that reverb time. The sound would simply escape, right? So as soon as we closed it, we were able to get sufficient reverb time, which was good. But what we saw was that this reverb time wasn't balanced. And so we needed to tune the materiality of the space in order to balance that reverb time, right? So these are the processes that like you would need to do as a designer in order to begin to understand and tune the acoustic performance of your space. So, you know, like the first concept, understand the big concept in terms of acoustics. Number two, set some performance criteria. Number three, have a appropriate model, do some simulations, and then basically balance the geometry, balance the materials to achieve your performance goals. So the other aspect to this project was this performative ceiling. So there was like these three different types of panels, which you saw on the first sketch, these reflectors, absorbers, and diffusers. And so this was this great excuse to sort of design these like fantastic looking diffusers for this roof surface, but also use this roof surface as a way to achieve this other performance goal, which was to decrease the sound level in the lounge area. So you remember there's two different areas, right? There's sort of the performance area and the lounge area. And so we wanted to decrease the sound level in the lounge area. And so what we did was we looked into optimization. It was me. I looked into optimization algorithms as a way to tune this roof in order to change the, to increase the volume in one area and decrease it in the other. And so I basically scripted a genetic algorithm in MicroStation VBA and was able to then tune this roof to optimize this number and distribution of these first reflections, acoustic reflections. And so you can see here, this was the performance improvement. On the left, we can see here that, you know, that it's quite loud throughout the whole space, relatively even, whereas after the optimization, we can see that it's in fact gotten louder on this side and, oh, here we go, louder on this side, increased volume, and decreased volume on that other side. So that seemed to have worked well. Just 1 second here. So I'm just going to go back to Teams here for a minute. I'm just going to, hey guys, can you see me? Yes? Okay. How much more time do I have? Just out of curiosity, can you hear me? Oh, you're muted there. 1 second here. I don't know how to unmute you. Hey, Hank.
Hey, you've got half an hour time.
Half an hour left, or
half an hour?
Okay, all right. I'm just wondering how many more projects. I don't want to like take up too much time or anything. No. Okay, great. Well, let us continue then. Okay, so I wanted to show that Pavilion for Dancing project as an example like of this student project, and also like as an example of these workflows that like you know many students would have to do in any type of acoustic project that they would have to develop. So this next project I wanted to talk about, which you likely have seen before if Jane Burry came and talked to you. This is a project that Jane was led basically at RMIT, which was the FabPod meeting room. And this project here, I also had the chance to work on with Jane and Mark and Nicholas and Daniel and a whole cast of other characters. So it was like really big team and so forth, but and a really enjoyable experience. And my contribution to the project was largely in the realm of acoustics, acoustic simulation, acoustic prediction, and how those might be able to inform this forum, right? And the project itself grew out of Mark Burry's research, Sagrada Familia. And when the Sagrada Familia's interior had recently become completed, many people were remarking on its great acoustics. And so Mark had this theory that maybe the hyperboloid geometry had something to do with it, right? So Mark comes to me and says, basically, what does a hyperboloid sound like? I don't know. But maybe it's a good question that we could try and find out, right? And so at Smart Geometry in 2011, I had the chance to work with Mark and Jane on this workshop that we ran together that basically investigated this question of what does a hyperboloid sound like? And so you can see here we've worked in a variety of different mediums. You can see the large one-to-one prototypes in the top of the slide, and the multiple laptops that were running simulations, and the scale models at the bottom. And so one of the ways that I was helping them investigate this question was through scale model measurements. So this was a technique that I had been working on as part of my PhD as well, in order to understand not absorption properties of materials, but their diffusive properties. So their ability to scatter sound in many different directions. And this is a important property of sound that has really only, in the last couple of decades, really been discovered to be of importance in architectural performance. And so this was the workflow that we were using here, was the digital model to 3D print to this measurement and analysis, and then those findings would then inform this final result. And this was part of this other research project, like I said, that I was working on, in which I was basically informing parametric models with this physical measurement. So here I did a range of physical models, basically looking at variations in depth and width of geometry and looking at the impact that those might have on the diffusiveness, the sound scattering properties. What I found was basically that, which is not entirely unpredicted, but that basically as the depth of the diffusing material increases, the frequency at which it diffuses decreases as well, and that as the width of those hexagons increases, basically less detail, the amount of scattering decreases as well. So deeper the geometry, the longer wavelengths basically that can impact it, and then less detail, less scattering. And so we used this as a way to develop this geometry for the Smart Geometry prototype that we built. This was the 1 to 10 test sample. That would become an acoustic surface, something like this. And then we sort of speculated okay, well, that's great. We can produce this, but can we tune it? Can we modulate this geometry or modulate this material over the surface in order to actually make rooms sound better, right? And so we had an opportunity to actually test this idea when the opportunity came to design this meeting room at RMIT. So this was the space. We had this long sort of open plan office in order to construct this meeting room. Regular meeting rooms sort of have these inherent issues with acoustics, right? So they tend to be square and small and made of hard materials, which gives flutter echoes between the parallel walls. Because of their squareness, they tend to have really pronounced room resonances. And if they have absorption, that absorption tends to be uneven, right? So either all on the ceiling or all on the floor or nothing at all. And so we sought to counter those by using geometry, right? So the room shape would help to reduce room resonances. The surface geometry would help to sort of break up flutter echoes, right, and diffuse the sounds. And the material distribution would help to distribute the acoustic absorbing material throughout the space where it was needed. Right on. Sounds like it makes sense. So how do we know that this is going to work though? And so this was sort of my research here, was integrating simulation in these 4 different ways into this project. And so the first one here is this separation of design and analysis. And this is very much like this traditional way that simulation is integrated into design. So that the architect does a design model, and then somebody, probably the engineer, then takes that and then makes an acoustic model which is suitable for simulation. That model is then simulated, and we get some sort of results in which we can then make some sort of recommendations for changing the design model. Now, this process is made a lot quicker if it is the designer that's actually controlling the simulation. The designer can then, through computation, make sure that the computational model is outputting the right acoustic model, making simulation relatively fast and efficient. But there's still like this separation of the design and analysis part. So I use Odeon simulation software for much of the simulation work that I do, and these are some of the types of results that can come out of it, right? And so what we're just seeing here is like this distribution of reverberation time, both inside the pod and outside the pod, and what impacts that has on the larger performance of the office itself. So the second workflow is this, I think, a bit more of like a holy grail of performance in architecture, right? Which is like this integrated analysis that's integrated into the architectural design software. And this is possible with the use of like plugins for Grasshopper and so forth. And in particular, Arthur van der Harden has developed this software called Pachyderm Acoustic, which I understand many of you have some experience with now. And so this is this example of this integrated design and analysis. And this, in a sense, it simplifies the process in that the design model is also the acoustic model, and the analysis can be done simultaneously within the design environment. What this also enables is like a computational optimization loop, right? That this would happen. And so we ran a workshop at RMIT, which we taught students to use Pachyderm, and they experimented with different shapes and so forth, and we sort of found that some shapes performed better than others. But I think that one of the sort of issues that we found with this was that the simulation software like Pachyderm and the simulation software Odeon are 2 different creatures, and so the results obviously are different coming out of the different softwares. So one is still very much different than the other. The third workflow would be this understanding of sound scattering. So the previous workflow that I showed for understanding sound scattering was using physical models. So making 1 to 10 3D prints, analyzing those, measuring those in a special lab, and then getting their performance coefficients, which is great, but it's a very time-consuming and costly process. And so we asked, like in this project, maybe there's a way to do this computationally. And so we used this process, or this computational idea called boundary element modeling, which basically discretizes the surfaces and pushes energy through that system, and basically understands the wave nature of sound in space, and therefore we're able to calculate the sound energy distribution from these different geometries. And so we're able to like get the scattering results virtually. And this is now, Pachyderm also does this now, as does some other softwares such as Reflex. And the fourth workflow is is related, but instead of using the boundary element modeling algorithm, using finite difference time domain and doing sound wave visualizations. And so here we sort of basically take our design model, discretize it into basically a voxel model, and then import that data into processing, and then we're able to get our results, which is a video. And so something that's really important to understand when we're designing for sound is these frameworks of rays versus waves. So most simulation software understands sound as a ray. And many times when we draw sound as a ray, so that sound is emitted from a sound source and then is drawn as a ray, which then can bounce off of a variety of different surfaces where the angle of incidence equals angles of reflection, so that we can precisely map where that sound is going. However, what we should always remember is that sound is not a ray. Sound is actually a wave, right? It is a pressure wave in a medium, and that medium is air. And so if we're actually going to understand sound, what we have to do is actually model the air that sound energy is traveling within. And that's how this sound wave visualizer works. So basically understands architecture in an entirely different way, right? It's much more akin to the CFD analysis or something. So we basically take our architecture and then basically discretize it into space. So here we're seeing like solid versus void, the solid wall versus the air of architecture. We then can sort of input that data into our finite difference time domain algorithm. We can then get these simulations, sound wave simulations, which can predict the sound scattering process. Because the sound scattering process cannot be really predicted using the ray-based models. And so what we see here is like a comparison of like a regular meeting room to the complex geometry of the fab pod meeting room, right? And so what we can see is that the flutter echoes are still quite distinct in the regular meeting room between these two parallel surfaces, whereas with the complex surface basically breaks up the sound wave into a much more diffusive sound field very quickly. So here's a couple images of that final project. You've probably seen before, both outside and inside. This is a project that I've done more recently called Spatial Sonic Networks, which was done with my collaborator and colleague Mitchell Akiyama, who teaches in the Visual Studies program at Daniels. And we were invited to participate in this art and architecture competition to create an installation for a courtyard at the University of Toronto. And so Mitchell and I are both interested in sound, and Mitchell was particularly taken with this idea of the sound as surveillance, right? And so these ideas of the parabolic form as a way of focusing sound, but also using that form, that focusing of sound, to be able to hear things that you shouldn't, right? So to be able to use that geometry as a way to surveil the environment in new ways. And so what we proposed was to create, in a sense, create like this analog communication network using these large geometries that would be placed amongst the site, right? So this acoustic geometry is performative urban infrastructure. So we had to understand the geometric logic of the parabola, which could be easily encoded into our parametric models. This is basically the Grasshopper script that we developed to create these larger surfaces, which would then have these focal points. And so each one of these would be like one node on the acoustic network, right? And so we needed to figure out like what that network was going to be. And so we wrote another script, this one in processing, that would be able to determine this this network. And we were very limited, sort of like where we could put these structures within this courtyard space. That being said, the design space was still rather large. And so this script basically predicted all of these different communication networks that we could produce, which we sort of selected our quote unquote optimal one. This was like many of the different options that we could produce. This was the network that was decided on. And this network generator could also be hooked up to our node generator. And so you ended up with all these very interesting acoustic mirrors that would be generated, right? One of the challenges with this was simulation, because the ray-based simulation actually doesn't work really very well for this type of geometry, this focusing geometry. So what we did was, again, use this finite difference time domain software to actually try and understand what was happening with this focusing phenomena. So here we can see these two simplified acoustic mirrors placed at some distance apart, and we can see like the initial sound wave being focused there, but this is where you see this really intense focusing for the sound wave, at which point it becomes another point source. So the sound starts here as the point source, basically becomes this planar wavefront. The direct sound arrives at the same time as that planar wavefront, and then the most significant pressure then is this focusing of that planar wavefront at the focus point. So we then had to figure out a way to fabricate this in a relatively easy way because we would be fabricating it. So we were using our CNC machine here. This is prior to getting the robot up and working, and then doing some physical verification of the geometry itself. And so here what we can see is that like at this focus point, we can see this sound level of about 95, which is about 20 decibels higher than the sort of areas that are only like 30 centimeters away, right? So it's like this vast increase in sound pressure at this point, which is what enables this surveillance or this communication to happen, because someone's able to basically sit at one node and talk to people at another node over great distances. And that's what the magic of this network, this acoustic network is. And this just sort of verified this result here. So this was the installation. And while we didn't win the competition, so we weren't able to build the full thing, we did win the People's Choice Award for that art project. We then got an artist residency the next summer at the Bentway, which is this large public space underneath the Gardner Freeway in Toronto, where we built some other sound installations, Mitchell and I. And we also imagined this much larger sound dish, which would then actually amplify the low frequency rumblings of the freeway above. Unfortunately, due to COVID, that project was supposed to be realized this year, and it is indefinitely on hold. But I'm certainly intrigued to see what would happen there, because it's one of these ideas that is really hard to simulate or to predict what's going to happen and what that sound might be like to like actually amplify those low frequency sounds. So another project I've been working on generally is the acoustic surface itself and these manipulations that we can do to the surface using digital fabrication. So robotic milling is one of the ways that we can manipulate the surface, and we've done many tests over the last couple of years on different types of surfaces that we can mill and what the impacts might be on the acoustics. So this was a sound diffusing surface that we installed in one of the meeting rooms at the university. We then sort of had the opportunity to test the room and so forth. And it certainly helps to improve the acoustics of the space. Also collaborating with a local mass timber manufacturer, looking into this prefabrication of acoustic properties within mass timber surfaces, sort of building on like that earlier research in understanding the nature of surfaces and their diffusive characteristics, and then being able to use the robot to prefabricate those. And finally, sort of this last idea that I want to talk about is this idea of acoustic gradients. And so this was a piece that we did a couple of years back that basically goes like this gradation from like a flat surface, i.e. acoustic reflector, to a complex surface, i.e. acoustic diffuser, to a perforated surface, exposing and absorbing underlayer, which will become an acoustic absorber. So this idea of like this continuous surface that could be tuned in many different ways is very intriguing to myself as a designer, where you sort of have this sort of single tectonic idea that can have these different acoustic consequences. And so one of my graduate students, Kiefer Savage, took this idea on and investigated this project using stacking, using the robot. And so his fellow colleague, student, Newton, did this project as well. So the two of them, Newton and Kiefer, basically shared a lot of the technology development for scripts for the robot, as well as end effectors for the robot. So the two of them worked together actually relatively closely, even though they had two totally different projects in the end. So robotic stacking, Kiefer was looking at this, his first semester was looking at simply stacking, like stuff like this. And the second semester has been looking at this idea of gradient acoustic performance. So the absorptive characteristic, one could space the blocks out, which sort of enables sound to be penetrating through the block layer. By shifting the blocks in and out, we basically create a diffusive surface. And then by placing those blocks, we can create different reflective conditions, such as those sound mirrors, which I just showed in the project previous. So here we see like the reflecting surface, right? So we can, through placing those blocks, we can create these different focusing zones or flutter echoes or whatever. And through staggering the blocks, we can create this diffusive surface. You can see here the reflection from the diffusive surface as it scatters the sound, both spatially but also temporally, like over time, and contrast that with the very specular reflection from the other wall. And then finally, we can space those blocks apart, which then the sound basically can just sort of travel through those sounds, through those geometries and be absorbed by the surface beyond. And what we can do is we can combine those three different ideas into a single surface. And so Kiefer not only had these like, or designed like a larger theater project that contained these different ideas, but also developed the robotic technology to actually fabricate this in one-to-one. So we needed to develop a custom end effector that combined both a pneumatic gripper as well as a vacuum gripper in order to have the strength to hold the wooden bricks to be able to push them through the saw, but also use the vacuum gripper to be able to place them in very tight proximity to each other. And so we built this custom saw table as well. So this computer controlled saw table, which enabled us to cut these blocks very precisely. And then the robot gripper could then hold them in the right spot. So it's like relatively complex application process that you can see here. There are certainly some efficiencies that, you know, if you were developing this for manufacture, you could tune out of the system. But I think, like, given that this is essentially like a simply prototyping stage, this is like completely admirable work that the team is doing. You can see it took several days to fabricate this final demonstrator here. So here's some shots, some photos of the different surfaces from that prototype. So hopefully what I've shown today is that as architects, like through our decisions about geometry and material, we inevitably impact the acoustic performance of our buildings, right? And so I think it's certainly our responsibility as architects to understand that our actions have consequence, acoustic consequence. And so we should take a more considered approach to sound and ask ourselves, like, what do you want your building to sound like? Given that you want your building to sound like something, what form will that take? Thank you. Okay, go back to here.
Yeah, clap really hard.
Okay.
Thank you. You also could hear then the poor acoustic performance of the space here.
Yeah.
Thanks, Brady. But it was a really, really interesting lecture, and we're very grateful to have the chance to listen to that. Are there any questions from the audience?
From the live audience.
The live audience? Are there any questions from the virtual audience?
Andrew's always good for a question.
Well, I would have a question first, particularly on your ongoing research in an urban context. So to give you some Sydney context, urban heat island is a big issue here. So if you live in an area where heat is quite a problem and you live close to a street as well, for acoustic reason, you probably can't apply cross ventilation because you then either suffer from the heat if you keep the window open, or you suffer from the noise if you keep the window, no, the other way. You suffer from the noise if you keep the window open, you suffer from the heat if you keep the window closed. Or another example, nighttime economy. So the city of Sydney is quite eager to boost nighttime economy, but on the other hand, you would have noise in the city, and if residents are there. So are these topics you're looking at the moment as well?
That's a great question. And I think this is like the whole discussion about architecture and noise in the city is one that's like so central to like our practice as architects, but also really, you know, very much like it's something that the public responds to like very intensely. So in Toronto, there's like a huge boom in building. It's like, well, I think like before the pandemic, it was like the biggest building site in North America. And much of that building was actually these large condo towers in downtown Toronto. And this is the exact problem that they're facing, right? Is that there's this huge problem with noise from the city, right? And so there's, and this is a very multi-dimensional problem. So I belong to this research group, the sound research group at the University of Toronto through the Jackman Humanities Institute that includes like, I think I'm the only architect on the team, but like you just really realize the multidisciplinary, multidimensional aspect to these issues, right? So like noise and the creation of noise is also within the rights of many people, and it has to do with the identity of different, you know, groups within the city. And so, and what some people consider noise, other people don't. It's very much part of their livelihood. And so it's a very contentious issue politically, but it's also clearly something that bothers so many people. And I would say, like, as an architect, we have to like obviously recognize like all of these like you know, I guess the values of the different sounds that are valued by the different stakeholders, number one, and where those are coming from, and what are the nature of those sounds, and who wants to listen to them and who doesn't want to listen to them. And the other thing to realize is that actually, you know, within architecture, we often have the ability to do some pretty amazing things with architectural enclosures and the tectonics of walls and structures and so forth to be able to contain sound in different ways. And one of the issues is that sometimes those cost money, right? And so like while, and not only do they cost money, but often they require like a certain care in their construction. And so what's happening like with the condo towers, you know, is like these issues of building acoustics where residents can hear each other, you know, where the sound gets transferred like through the structure, through the walls in different ways. And we have the technology to deal with that, right? Both like in terms of like the transmission of sound from unit to unit, but occasionally mistakes are made either in the design of these structures by people who are just not familiar with what they need to do to prevent that, or in the actual installation, you know, like if you cut a hole for an electrical receptacle, right? You can actually like create essentially a hole which sound leaks through. And this is one of these issues that you need to understand, like that sound actually, in this case, acts more like a liquid than a ray, right? And so like this liquid sound just sort of seeps through all the cracks and gets into these other parts of the building. In terms of sound from outside, you know, we can build while, again, this is kind of like this liquid that can just sort of seep in, we can still build like acoustic mufflers and so forth that would greatly decrease this if we so desired. And so I think that there's like a great deal of research that can be done and should be done. That my research tends to focus more on like these computational and practical aspects, but I think that this is a huge issue. And like, you know, working with mass timber now, the Daniels architecture faculty recently joined with the Forestry Institute. And so we have this new Mass Timber Institute, which I'm fortunate to be part of. And one of the issues with mass timber is that it is not as good of an acoustic isolator as concrete. And so so while it has like this great sustainable characteristics, its acoustic characteristics are not as good. And so we're sort of currently right now searching for these, you know, design material tectonic solutions that can help us in this pursuit of controlling sound in a better way.
Good, thank you. There's another question from Andrew Butler in the chat. I either can read the question or you quickly can. Okay, so fantastic analysis approach. So the question is really, what do you think will happen to the consultant landscape if these tools become more accessible to amateur engineers?
This is a great question. This question comes up almost all the time. And sometimes it comes up as, you know, like, you know, engineers, you know, voicing concern that these tools will be misused or that this will take away the jobs from engineers. And I would say that in my experience working at Foster and Partners, my experience working at Bear Happel, and my experience working in these multidisciplinary research teams, is in fact the opposite happens. Is that through like the use of these simulation tools, these tools that introduce performance into the design environment, we as designers become more aware and better able to ask the right questions about performance. And so we're able to push the designs into like realms that they weren't before, and as a result, give engineers and our other consultants much more interesting problems to deal with, right? And so that is what I've found in my experience. So this is speaking professionally from my experience, not from any academic study that I've done, but hopefully that answers the question.
No, Andrew does it. Andrew, you cannot. Yeah, big nod from Andrew. It's probably a similar thing like with, you know, Caramba allows you to do structural optimization, understand structure better, but it didn't really take away the job of the structural engineer, but give him more interesting problems. Ladybug, you know, for solar and so on, I think so. Would be quite good. Is there a last question from anyone? Yes. Yes, come down.
And Leo's got a question as well.
Just, you know, ask.
Hi. So you've talked about tools that can measure conditions in digital environments, like conditions like reverb. But if you replicate the digital environments physically, are there tools that can measure the same conditions in the physical environment? And do the results match up? Just to test if like the digital tools are accurate to real life.
Yeah, that's a great experiment or a great question, and that is something that we endeavor to do in our projects. And you know, I would say like there are some parameters, there are some types of acoustic performance, some aspects of acoustic performance that are, I would say, like easier to simulate and measure, and therefore validate and verify those workflows. And so reverberation time is one of those acoustic parameters. So, and this is an exercise that I do with my students that take my acoustics course with me. what we do basically is like model or measure a room like dimensionally, use calculation tools to predict the reverb time. Then what we do is we build a virtual model of the room and use something like Pachyderm or Odeon to simulate the performance of the reverb time. And then what we do is we bring my acoustic sound meter and speaker and microphone in, and then we measure the acoustic performance, the reverb time, and we see how those things match. And you know, I think one of the good things is that they usually do. So reverb time is one of these things where we can easily verify and validate among the calculation, the simulation, and the measurement. There are other aspects of acoustic performance that are we're currently challenged a little bit more to do that with. So I talked a bit about sound diffusion and sound scattering, and that's something that's a little bit harder to measure and simulate. And so that's something that I'm currently spending some time on to do that. Basically, similar as the focusing, the sound focusing work. That's something that the current simulation tools are like challenged to simulate, and so we have to. So the actual like prototyping and measurement was actually one of the best ways to actually verify that worked, right? But yes, so generally most acoustic parameters we can both simulate and verify, and that is something that we aim to do.
There was one last question. Oh, did you have another?
No, that's
There's a question from there's a question from Leo. I don't know if you can see the chat, Brady, but Leo's asking you, firstly, he said fascinating lecture. He's asking you what the transition was like from moving from professional practice into academia. And he also wanted to know if you've got any career advice for our students. This might be quite a long question.
Okay, yeah, that is a good question. And you know, the transition, transitioning from professional to academic, I would say it was terrible. No, it wasn't terrible. But it certainly was not something I was, I don't know what I was thinking, to be honest, leaving practice, but I did. And I really enjoyed practice, and I really miss practice. So that's something to say. That being said, in my current position as an academic at the University of Toronto, while I find the job challenging, I would say that I am never bored. So that there's always like so many like really interesting people that I meet and interesting problems. So the scale of projects that I get to work on are generally much smaller, but usually a lot more challenging. So the transition I think was, I don't know, not necessarily like easy, and certainly I miss it, but yeah. In terms of career advice, that's a good question. I think what I'm currently seeing, like in the academic, in the variety of academic schools that I'm familiar with, and in terms of professional careers, is that like when I graduated, there was none of these specialist programs that you could go and do. If anything, you went to Harvard and got a post-professional master's, but that was just more of like a rubber stamp or something to show that you'd gone to Harvard. But now there's like this wonderful array of these different master's degrees and PhDs that enable you to explore computation and design in a new way. And I think, like, I don't know if this is advice, but certainly, like, if I was graduating now with my architecture degree, I would probably if I was interested in pursuing computation or digital fabrication, I would certainly look to one of these post-professional, more advanced degrees as a way to skill up before probably entering practice.
Masters of philosophy, with us.
The other thing I would say is that I think there's also like probably a lot of potential not in branching out from architecture. There's a lot of interesting fabricators within like the city of Toronto that hire architects and people who are, and they're the ones that are actually buying robots and buying amazing 3D printers and buying these like really expensive CNC milling devices. And so if you really wanted to get into that, I would say you'd probably go into potentially manufacturing or at least design build type projects.
Yeah. Are there any last questions? Or can anyone see the chat on my computer for a question?
I've got a question in the chat.
Yeah? Oh, you put one in?
Yeah.
Yeah. Should we have one more? Because we are going over, yeah. But I think we can. It's good. It's all good. It would just shave a couple minutes off your presentation.
Yeah. So the last question would be, Brady, do you see the user experience of Pachyderm improving in the future?
That's a good question. So I've been using Pachyderm for a long time, and as a result of like knowing about Pachyderm, I guess intentionally don't use it. I tend to use Odeon for my simulations. Odeon works faster and has like really much better graphics in terms of output of results. That being said, like I know Arthur van der Harten very well, the creator of Pachyderm, and Arthur currently has some new initiatives where he's really trying to get some money to invest in the development of Pachyderm, but also gain some new academic partners and industry partners that might help contribute to the development of Pachyderm. So yes, I do see Pachyderm improving in the future, and I would really like to help Arthur improve Pachyderm in the future. And I would also invite any of you who are interested in improving Pachyderm to get in touch with Arthur and see if there's something that you can do to help it, because it's something that really, if it was improved, could really give a lot back to the community of architects who are interested in integrating sound into their designs.
And I really do think that's like developing the tools to do that is the way to build a better understanding of architectural acoustics in that earlier stage of the design. And you talked about we have a responsibility to do that, to take account of all the phenomena, all the environmental phenomena, and really bring them together. And I do get a sense that sound is sort of left off the table. And it's great that Pachyderm exists, but it would be, it could be a more competitive landscape, I guess, for a plugin that addresses that particular analysis of that phenomenon. So I think that's actually really good career advice to end on. That's an opportunity right there. So you can see how engaging with these tools opens up to thinking about how you can improve them. And yeah, I think the user interface is such a massive issue as well that we have to deal with across all of the tools, digital and computational tools we've got at the moment. It's a big challenge for the future going forward.
So please extend greetings to Arthur. We are happy to help out if there's any.
Our student Mindy has been in contact with Arthur, yeah? Yep, and she was using Pachyderm during her project this term. So there you go, some opportunities there. Was there a last question in the chat? I heard my a ding ding.
No.
No, okay. So do you have any last questions? No? Okay, so thank you so much again, Brady. We are going to have to move on because these guys are ready to present their final projects and ready to graduate as well. So we really appreciate you joining us today from Thursday. Awesome. And it's been great that we've been able to establish this connection in, I hate to say it, these really weird times. This has been a really nice outcome. And actually, I think this hybrid thing works okay, yeah? Yeah, so this has been a great opportunity. Yeah, and a really interesting presentation. Thank you so much.
Excellent. Thank you for inviting me, and thank you for listening. It was really great. Okay. Bye, everybody.
Bye. So now we're going to move on to the student presentations for today. Yep.
Yeah. Okay, so the half of the group, Daniel will come with me.
So if you check the schedule, guys, if you're in session 2 or 4, then you're upstairs in level 1. Yep, and if you're
Good. There you go. Good luck.
Okay. Yeah. Is it? Okay. I was like, oh goodness. Okay. Yay! I'm actually super excited.
You need a mic.
I need a mic?
Do you need one?
Is it easier without? I can just project. Just yell, it's alright. Is my face showing in this or no? Okay. I was like, I don't know. Oh,
Test 1, 2.
there we go.
That's good. It's all right. It's only us. Yeah, it's like talking to your friends.
Yeah. No, you're okay. Alrighty. Alright, ready to go? Alright, lovely. So hi, my name's Ebony, and for my graduation project, I have decided to go with the topic of shaping social housing within Sydney. And my research topic ended up being connecting communities and data and generating an interactive spatial decision support tool for social housing stakeholders. So the issues I wanted to address was, one, the increasing number of people experiencing homelessness in Sydney, and two, using and harnessing the exponential amounts of data, and three, produce a tool that enables communities to not only understand, it's muted? Okay. All right, not only understand, but also include communities in the decisions that impact them. So in Australia, according to a survey by Wesley Mission, over 60% of Australians believe that homelessness is due to people being addicted either through drugs or alcohol. However, in reality, 90% of people experiencing homelessness is due to unsafe dwelling conditions. So how can this perception and understanding be changed? It is also actually proven that it's cheaper to try and solve homelessness than try to manage it through policing and hospital bills. So why is there nothing being done? So the objective for my project is to generate a tool that uses data to educate communities and humanize the data and the outcomes, where hopefully better understandings are also generated. So it's a tool that aims to change behaviors. So the 2D and 3D interactions within the tool would allow for new perspectives and new interactions spatially and numerically. So the tools I ended up using started with Tableau and gathering some 2D contextualizations and generating understandings for myself and where I'd go from there. Then using the 3D data in Grasshopper and having the 3D spatial outcomes from there, and where I could start testing the prototype for the tool. And I used the Bano to incorporate the 3D data, and decoding spaces was used to output the data into a JSON, and then finally presenting it onto Mapbox in an online environment. Just to look at the workflow more specifically, so as you can see, I started with 2D contextualization, starting with census data and homeless data, and gathering outputs from them into Tableau. And then I worked on the 3D contextualization and offline prototyping, where Urbano, with the implementation of 3D data from 6maps and OpenStreetMaps, allowed for 3D translation in Grasshopper. And then I could start prototyping and developing a tool that could be used by user groups. So the input parameters I ended up going with was one, the amount of developed cadastres or areas, the heights of the buildings, and also I ended up adding later on if it would be single dwellings or double, like 2 people dwellings. And from there, the outputs would be the estimated amount of people that would be housed, the estimated amount of dwellings, the amount of buildings that would be generated, and also an uncontrolled variable would be the distance to a train station. So yeah, I had some things that users couldn't control, like I wanted to keep things within an 800-meter radius of the train station so people could actually have accessible transport points. And yeah, so then moving on to the internet accessibility part. So I used the coding spaces to convert it into a GeoJSON and therefore present it in an online environment that was accessible for multiple user groups to actually interact and use the tool. So this here is probably one of the best maps I was able to get out of Tableau. It presents the correlation of clusterings of homeless people, so people experiencing homelessness in Sydney. So you can see like there's like a direct line there almost, where people explicitly in those areas. So this is from the 2016 census data. So from this, I needed to choose an area which I would specify and use further on in my 3D spatial data. So the area had to currently require social housing, have points of accessibility for transportation, and also avoiding any of these clusterings of these dark blue areas. So from the data, the best fit for this was Parramatta, and more specifically the area around Parramatta Station and Harris Park Station. And this area also actually had appropriate 3D spatial data that I was able to incorporate into the tool, which was also important because not all the areas around like Blacktown necessarily have data presented. So it was important that I needed an area that actually has data available to me. So getting into the correlation and the representation of the spatial data. So this was OpenStreetMap's data when I was able to get into Grasshopper. So this was used with Albano and translating it with metadata, and it showcased important like amenities and features along with detailed roads, cadasters, buildings and their heights. Yeah, so this was super good. It was amazing. So it allowed for like my own understanding, but also users to understand the spatial context for this. And the next one, I overlaid it again with 6 maps, again with Urbano, and this came in as a shapefile. And this just gave even more detail. You can see it's extremely detailed cadasters, but it also had roads, and this one also had train lines, which is important as I needed points of access for my train stations. All right, after I got that, I was able to start prototyping the offline prototype, essentially. So yeah, as I said before, the train stations identified with that arrow is Harris Park train station, and then the Parramatta is a little bit behind them. And just to go into more detail, so I had to use cadasters only within the 800-meter radius from that train station, as anything outside that would be more than 10-minute walk. And I found from research, anything more than 10-minute walk generally wasn't applicable for people to access in regards, especially when you're designing for people who may not necessarily have means of transportation by themselves through a car. So having points such as trains is important for this. I also needed to ensure that the cadasters weren't clustered together. So it actually showed a range of the hypothetical scenario where if you have everything clustered in one area, it won't really show a range of opportunities. So I needed to avoid any clusterings. And outliers such as cadasters that were way too big or way too small were removed from the data set as well. Unfortunately, I did have some missing data. As you can see, I've got like massive blank spaces, but these blank spaces were just essentially used as an opportunity for options to develop. Were used as options to develop social housing within Sydney. So here's just like a simplified version of my script and the inputs. So the red being the inputs, yellow being like the controlled aspects that I put in, and the blue being the outputs. So all the calculations were done from the New South Wales Land and Housing Corporation design standards in 2014. Initially, as I said, I started with single dwelling apartment types, as those are actually the most needed in Sydney at the moment. So that's what I ended up starting with, but I thought it would be good to show options. So I added in the second dwelling type as an option as a generated output. So careful consideration and sensitivity was needed in order to generate portrayals that both experts and decision makers, but also communities could understand. So it was quite difficult trying to generate simplicity, but also some complexity at the same time, if that makes sense. So yeah, I was able to put this into an online prototype. So this was just to allow for accessibility and a place for communication between decision makers and community. It was planned to be an interface for both user groups. So online space seemed like the most plausible option for this. So getting the 3D geometry into an online space required me converting the buildings and all the 3D data into a GeoJSON file format, and then that was allowed through the Decoding Spaces plugin. Yeah, and JSONs allow for like online interaction and accessibility and visualization. So yeah, so once I was able to get the GeoJSON correct and accurate, I would put it to the tile sets, and then it therefore was presented in a 3D online context. Limitations and future implementations include, so unfortunately the tool is not completely fully polished. So here's what I would like for like the user interface to be look like. But so that would be like the next step I would take after this. But because of the 10-week time constraint, I wasn't quite able to get there. And the user interface would allow for some user testing and feedback from there, and I'd be able to work from there and generate hopefully even better understandings from this. Some unseen issues included like messy data, and Urbano's transformation and metadata messed up a lot of portrayals in Grasshopper, which is super fun to work with. And GeoJSON issues including like EPSG translation, which is like the origin point. So when I was initially trying to get it into an online space, it was being projected in Russia, completely opposite side of the world from where I needed it to be. So in future implementations could also include, like, we have a new census next year, so more updated data would be really vital for that, and also incorporation of real-time data as we move into future cities, and designing for communities and representations of those communities for them to understand, I think is a very vital aspect. Yeah, and that's everything I have. Thank you.
I have a question.
Yeah.
What do you think your sort of key learnings? What have you
The dichotomies between user groups that I chose for this was very large, the opposite ends of the spectrums. However, I think a tool allows for the space for like integration and understanding from both ends, possibly. I couldn't test that in the tool, but at least trying to design a space for that in the future to work is, I guess, important to try. Did that answer your question?
I think it's like, yeah, what, like, maybe it's a little bit hard to understand right now what you've learned because you're too close to it still. But yeah, just interesting, even from a process perspective, like what sort of how do you think your data literacy skills will improve over the process of that research?
So I definitely had to simplify a lot of it too for someone who's not an expert, especially in the translation, because I ended up initially starting with some really complex and a lot of outcomes, and I'm like, this is not necessarily meaningful for everybody, so I had to cut down and just try and just work with simple things at the beginning, and then see how it goes in the future, possibly. Yeah.
How have your industry partners responded to your feedback?
Feedback from my industry partner. He really wanted me to try and get to that interface part, but I at least got like a plan set out for where I wanted to go in the future, possibly. Yeah, there's just like a lot of unseen issues, which really was unfortunate, but I got into a place I was pretty happy with in the end result, where I got it kind of working online, where you could interact 3D spatially, which is interesting on its own.
Yeah, fantastic. A really, really focused project.
Yeah.
Using OSM data is really good.
Yeah.
So do you think, if you had a complete data set from the very beginning, your processes, the way that you scripted it would change a lot?
Yeah, so it would definitely have changed because Urbano it's great just getting it into Grasshopper, but however, translating that back out to the online space was a nightmare. So
what's the biggest limitation
in the OSM system, probably the lack of data as well. Unfortunately, with OSM, like, there's not much 3D projections. I actually had to make my own dummy data set to actually have it look like a contextual place. I had like, I think 11 buildings, but I ended up just presenting more just so it looked like a city. So I think it would make more sense for a user. Like this is a city, not just like 3 buildings, as an example. So I think it would be more accurate if there was more, like the correct present relation, I think. Is that? Yeah. Yeah. Okay. All right, awesome.
Do you know how to stop it?
No, it's just press escape.
It's not.
Oh,
Yeah.
Don't forget to share your screen. Otherwise, our friend, we need to share it between. Otherwise, they're not going to see the slide.
Okay. Good. So, hi, I'm Emily, and my research project is evaluating the new normal. So how machine learning can be used to evaluate social distancing regulations in public spaces. So the ongoing impact of the coronavirus pandemic has directed significant focus on maintaining health and safety through physical and social distancing measures. Social distancing is maintained through reducing the rate of contact with other people and has proven to be effective in preventing the spread of the virus. Social distancing has wide-ranging implications, from travel bans, capacity limits, to new working from home arrangements. This is becoming the new normal, and to ensure these measures are followed, social distancing patterns need to be monitored and evaluated. So how can machine learning be utilized to spatially analyze real-time data to detect social distancing in public spaces? This research project aims to create an AI-based monitoring system utilizing real-time data to identify and evaluate social distancing. Real-time data monitoring can be applied to evaluate how effectively people stay the required 1.5 meters apart in public space, and potentially allowing for better management of the distribution of people. The objective of this research is to create a system that can be implemented anywhere to quickly and effectively detect social distancing within spaces, allowing us to understand and analyze physical distancing patterns. For my case study, I looked at an analysis of pedestrian activity before and during COVID-19 lockdown. Webcam time lapses were used with machine learning, and the hourly time lapse from webcams are used in this study to estimate how pedestrian activity changed during COVID-19 lockdown. In the first stage of the analysis, a state-of-the-art machine learning algorithm called YOLO was used to detect people. And they split the HD image into smaller tiles to increase the number of detected pedestrians by over 50%. The presented method allows for more efficient detection and counting of pedestrians. And they compared 4 different machine learning platforms, which I later tested. This is my workflow. And the main sections of the prototype development include the camera setup and the script development. So with the camera setup, it utilizes an IP web camera application on your smartphone, and then you set the camera to fixed location and copy the IP address into the website that is developed using JavaScript. I use TensorFlow as a machine learning platform to detect people, and then a Euclidean distance formula to measure the distance between people. So the first stage was setting up the webcam. I decided to use a webcam application because it's available on Apple and Android,
It's easy to download. Anyone can use it. It can be used anywhere, and it's just a really easy way to get a live video feed. So the steps for this included downloading the application, setting the camera at a fixed location, and then opening the app and copying the IP address. And next is the workflow for the script development. So this included applying object detection to identify all people within the video frame, computing the Euclidean distance between all detected people, and then based on these distances, check to see if any two people are less than n pixels apart. I don't know what I've done.
That's okay. Oh.
Just unclick recover and restart. Welcome to that. Back to Teams. Yeah, you're good.
Oh, I stopped sharing content by accident.
So you're not screen sharing. Now you are.
There you go.
Good.
Yeah,
Okay, thanks.
Sorry.
Okay, so this is just the basic JavaScript web page that I developed. So at the top, you enter your IP address, and then it loads the video. So that's sort of that there. This is for the machine learning. So I tested a couple of different machine learning platforms. The first one, I was intending on using Runway ML, which is sort of an open source platform where users can create machine learning models and anyone can use them. But with this, you had to have a pre-recorded video that you loaded in and then it found the people. Where I was really hoping to do a live video feed. So then I decided to use TensorFlow. So TensorFlow is an open source machine learning platform that can be called upon in JavaScript to use object detection. And this was just testing it here. So next was creating the bounding boxes. To do this, I created a canvas, and then using TensorFlow, I found the 4 furthest points of people and drew a box around it, and then found the center point. This took a bit of testing and debugging to get it exactly right. Next was measuring the distance. So to find the center points, I measured halfway down and halfway across each bounding box. And then setting the camera at a set location, I found that a 1.5 meter table equaled 200 pixels. And then to measure between the center points of people, I used the Euclidean distance formula. So if people were further than 200 pixels apart, they were green. If they were closer than 200 pixels, they would turn red to sort of alert that they were too close. So first for testing, because I couldn't go into the office because of COVID, I just used some still images on the internet. It was seeming to work okay, but I wasn't sure how it would go with live video footage. So here is the first sort of testing I did in my office space. Everyone was really excited to help out. So it was working as expected, but one factor I hadn't really thought about was depth. So if people were on the same line, it was fine. But yeah, we had a little bit to consider with the depth factor. So as the detector uses pixels to define distance, there's currently no depth factor. So we found that this could be estimated using the Y value of an object. So the higher the Y value of an object, the closer they are to the camera. This wasn't completely accurate, but with the time frame, this is sort of what was our solution. So this was then testing it again in my office space. And then we just had the console panel on the right, which shows all of the data that's coming through. So whilst the tool that I developed does align with the aim and the objectives of my paper, it should be noted that for the most accurate results, future development should include camera calibration through intrinsic and extrinsic parameters to allow pixels to be mapped to measurable units, Whilst delivering an approximated analysis of pedestrian movements, currently pixel distances are strictly relied on, resulting in less accurate findings and data. So for an even more accurate evaluation, a top-down transformation of the viewing angle could be implemented, allowing for the application of distance calculations to the bird's eye view of the specified space, leading to a better approximation of pedestrian distances. So this tool can be developed on a larger scale, with cameras potentially being set up on drones to monitor and analyze beaches, parklands, or railways. The tool could not only tap into stopping the spread of disease, but also be used to evaluate how spaces are used, if they are being used effectively and efficiently, and how they could be reimagined or redesigned to better accommodate people. Further factors that could be considered include privacy protection of pedestrians, depth sensing, and providing a pedestrian count, as well as seeing what else we could use machine learning to detect, like whether people are wearing masks. So revisiting my initial research question, how can machine learning be utilized to spatially analyze real-time data to detect social distancing in public spaces? It has been proven that through machine learning employed through JavaScript, pedestrian patterns can be detected in a space. Whilst this is only the foundations for potential future work, as practicing social distancing is now the new norm, I think it's important to identify and evaluate pedestrian patterns in public spaces, just for designing and planning for the future. Thanks.
Do you think that's a way to potentially use stereoscopic vision for detecting
Yeah, definitely.
instead of having something like the space?
Yeah, I think that could be a way. I didn't really study into that too much. I looked at more like, yeah, pixel mapping, but I think that's definitely something that could be implemented.
Have you considered using depth detection to establish the wide
Yeah, I did look into that, but it seemed like it was going to be a lot of effort and take quite a bit of time. But yeah, it's definitely something that I would like to further look into. Yeah, definitely. Yeah, it's popping up. Yeah. But yeah, I think there were so many factors that I didn't even think of when I started this. And I was like, oh yeah, just find the distance. And I was like, there's so many other things to sort of include. So I would like to sort of take this further and figure out the depth and test it.
There's a number of technical issues that obviously have to be resolved. What about, the ethical issues?
Yeah. Well, it's interesting now that I think as of yesterday, they said clubs and places like that can reopen.
Yeah.
So I've been trying to make sure that this research is still relevant.
Well, I think the way you framed it at the end is absolutely critical, because it's not, you're not developing a tool for surveillance purposes, like alone. You're developing a tool that can be used to enhance our knowledge about the way people live through and use any environment. But I think obviously with that comes a responsibility to think about how we deal with people's personal data.
Yeah.
Like, we all feel comfortable just sitting here being, I mean, we are being surveyed. That camera up there, but technically that data is not supposed to be shared. So actually, that was my question to you. Who's the user of this tool in your mind?
So I think my initial sort of target audience was office spaces. So during COVID, I couldn't go into work very much, and there was a lot of focus placed on moving the desks around and how many people were allowed in one space at a time. So that was sort of the initial user. But I think it could sort of, yeah.
Yeah, so people who really need to comply with regulations or make sure office environments, occupational health and safety.
Yeah. Yeah, and then even if like at cafes or restaurants, everywhere sort of has a COVID what are they called? A COVID marshal, yeah. So it would be a lot easier if they could just sort of sit at their desk and kind of monitor the area. And then if they see that people aren't sort of adhering to it, they can go down and
Yeah, and you can imagine that also that, I don't know, if you look into your own desktop, where everyone can have a dashboard.
yeah.
Like the
It's very dystopian.
flash red.
Yeah, it's getting very dystopian.
Yeah.
Well, that was sort of the idea with using the smartphone application, because it takes like 2 seconds to set up and you can put it anywhere. It's been fun just sort of going around and just sitting at places like, yeah, it's really accessible.
Awesome. Thank you so much. We're going to keep moving on.
Thanks.
I guess I'm just going to hold it.
Is it still sharing? Oh, yeah. It's flash it.
Oh, no, that's your email. Oh, no, here we go. Good. Yeah, your email was just all over the screen.
Yeah.
Okay.
Go for it.
Hi all. My research project is about urban greening. Do you want to turn it? My research project is about urban greening. So what is urban greening and why should we all be promoting it? Well, urban greening is simply growing plants in urban spaces, and doing this helps the environment in many ways. A green rooftop can be up to 3 degrees cooler than a typical concrete rooftop. It also cools the city as a whole. It improves air quality. You can grow fresh fruit and veg closer to the shops. It can lure fauna back to the city, and it can help restore what once was bush. So there are all these benefits if we have urban greening, but first we need to make sure the plants actually grow well. Currently, we leave the design of urban green spaces to landscapers. They decide what to plant where based on knowledge and intuition. But the urban environment is a very complex environment, and the success of a plant is based on how the climate interacts with structure. Luckily, we as designers have access to a range of climate and building data that I aim to develop into a tool that more reliably estimates what plants should grow where on the rooftops and the facades of an urban site. The aim is to make this a robust and fast tool that is accessible to designers in the AEC industry. So how do we figure out what type of plant should grow on a specific space on an urban site using this data? Well, plants have needs, and depending on the type of plant, grow best at a certain amount of sunlight, soil, temperature, water, and humidity. Using climate and building data, we can find out how much sunlight a space is exposed to, how big of a load the space can take, what the temperature of the space is, how much rainfall the space gets, and what its humidity level is. Then we can compare the conditions of the space against the needs of the plants and find out what type of plant is best suited for the specific space. It's not going. Okay, wait, sorry. So now we know how to suit a plant type with a space on an urban site. We can plan how to make it happen. This here is my workflow diagram and is broken down into a series of inputs that are processed by a Grasshopper script into more meaningful outputs. First, we need a 3D model of an urban site to test the tool on. My industry partner, Tony McDonald, had a model of some buildings surrounding Central Station on hand. This model had a lot of buildings, so I chose a section of it and separated it into the site I want to analyze and the buildings surrounding it as the site's context. Most analysis tools in Grasshopper work much better with simplified geometry, and this model came to me as a messy mesh. So what I did was I took the curves defining the rooftops of the buildings, simplified them into polylines, and then extruded them to the ground to create a set of building masses. The aim of the tool is to suit a space on a site with a plant type. So I gridded the building masses uniformly, where each grid cell is a space to test for a plant type. To make sure the tool is adaptable, I made 2 locations for the site, one in Sydney CBD and one in Nanham, Queensland. This way we can clearly see if the script is doing its job right, because Nanham has a very different climate to Sydney. Now, obviously we can't just plant plants wherever we like. There are windows on facades and stuff like plant rooms on rooftops. So to replicate this, I separated the site into available spaces and non-available spaces, where only the available spaces would get tested for a plant type. Also, plants need soil to grow, and soil can weigh a lot. Discussing with Tony, we estimated that soil weighs around 1,800 kilos per cubic meter, and existing multi-story buildings can take around 400 kilos per square meter of rooftop and 60 kilos per facade. Taking this into account, I populated the rooftops and facades with max loads they can take, just so there isn't something ridiculous like a gum tree suited with a facade space. Plants also need sunlight, but on an urban site with heaps of buildings everywhere, it's hard to know how much sun every bit of space is getting. Luckily, Energy Plus stores weather data into Energy Plus weather files. These files can be processed in Grasshopper with an analysis tool called Ladybug, which in my case was used to simulate sun paths and rays to find out how much exposure each grid cell gets per day on average. We can tell that the sunlight analysis is working right because Nanham's site is overall getting more sun exposure than Sydney's site. This makes sense because Nanham is much closer to the equator than Sydney. The Bureau of Meteorology stores a bunch of climate data in the form of climate maps. These maps are color-coded, with each color corresponding to a certain climate value. I use the annual temperature, rainfall, and humidity maps to find out what the climates are like for both sites. At first, I just grabbed a pixel-based format of the maps and tried to find out the closest pixel to the site points. This method wasn't accurate because the closest pixel to the site point may not actually always be the area the site point is truly in, and the only way to make this method more accurate was to increase the resolution of the image, which increased the computation time. Luckily, the maps also came as vector-based images. Using the vector curves, we can find out what curve the site point is truly in, and then find the curve's corresponding color and climate value. On a site, spaces receiving more sunlight are warmer. Spaces with a lower altitude are also warmer and more humid, and rooftops generally get more rainfall than facades. So this is mapped onto the site model. Now that we have done all our analysis, we can compare the results to the needs of the plants. I made a mock-up data set of 15 plant types and their needs of soil depth, sunlight, temperature, rainfall, and humidity. But if a user is using the tool, they can choose what plants they want to grow here. For example, they can choose they only want native plants or they only want edible plants. So now we have an analysis value for each grid cell on the site and a set of plant types and their needs. To find out what plant is best suited for each grid cell, we can subtract the plant need values from the analysis result values. Because each value is in different units, we need to reparameterize them so each value is weighted equally. Then the values are added together for each plant type. Simply, the plant with the lowest score is best suited for the specific grid cell. The plant with the second lowest score is second best suited, and so on. The reparameterization part is really important here because it determines how much each condition is weighed into the final plant score. If a user knows they can water their own plants, they can weigh the rainfall value lower than the rest. Or if a user is building a new site, they can design the facades and rooftops in a way where they can take as much load as they want. In this case, they can weigh the soil value lower than the rest. Now that we know what plant is best suited for each grid cell, we can visualize the results in two different ways. The first, if a user wants to know which plants they should grow where, we can show the best suited plant type for each grid cell, which is the ones on the top. Here we can see that both Sydney and Nanham share the same amount of plant diversity, but are better suited for different plant types. The second way is if a user wants to know where the best spaces are to grow a specific type of plant. We can then show the site through a heat map where the hottest spaces are where the plant is better suited. For the Tecomantrophilia, the Nanham site is better suited than the Sydney site because it has more red areas. So we have a bunch of results, but where do they fit into the design process of urban greening? Well, landscapers can use them as data-based evidence to inform design decisions, or we can just skip the landscapers altogether and just plant the type of plants the tool recommends. Alternatively, the results can be fed into Groundhog, which is a tool that can simulate the growth and interaction of the chosen plants over time. Now, this was only a 10-week project, and there's still a lot we can do to improve. Currently, the tool just uses average values, but if we compare the range and distribution of the plant need data against the climate data, we can potentially suit plants that have specific needs with more stable climates and suit plants that can survive in a wide range of environments with more fluctuating environments. For plants, an important element that I did not have time to investigate was wind load and direction, but with more time, this can be analyzed in Grasshopper with tools like Dragonfly or Eddy3D. Some of the variables in the script are currently being estimated, but with the help of a botanist and a meteorologist, we can make sure the tool is giving more reliable results. We can also store the site's coordinates using GeoJSON and incorporate GIS analysis. Lastly, to deliver this tool accessibly into the AEC industry, I'm planning to either package it as a Grasshopper plugin, it's going to be called Lorikeet, or as an application on an urban virtual modeling platform like Giraffe. Okay, so with the help of computation, designers are more influential than ever. And it is important that with such power, it is directed to solve complex real-world problems. My research project outlines a data-driven way we can more accurately suit plant with spaces on an urban site and is an advance in the designer's mission to empower urban greening. Yeah. Thank you. Basically, I went on Google Images and searched up buildings, and obviously, like on facades, most unavailable spaces are windows. Like you can't plant plants on windows. And on rooftops, there's like a range of unavailable spaces. So it's seeded randomly where these unavailable spaces are, but the randomized script tries to replicate the unavailable spaces in real life. Yeah. Oh wait, that's the wrong slide. Yeah, you can see the red spaces sort of look like windows. Yeah.
I have a comment, not a question. Awesome presentation. the relevance and the importance of what you're doing. I think that your mic drop, your last two sentences, are great, and I'm sure you just like when it's Nicole. That's what I really want to hear, that we can use your skills and the power of computation to address real world, complex, pressing issues, and we can develop a better relationship between us and the environment that we live in. I just think it's so important. So well done, and I think your work should be presented to the landscape architecture.
Yeah.
We're going to find a way to do that, because I think they need to be perspectives.
Yeah.
Sure, I would happily do that.
Oh, do you have anyone else?
I mean, I've seen this project from start to finish, so it's finished really well. I think you did a really good job. It's a bit of an irrelevant question, though. How many plants did you buy during this time?
How many plants? Oh, we have like a huge backyard garden at my place. So we usually buy the seeds and plant them.
Oh,
Yeah.
okay.
Yeah.
Wow.
So you're like,
You grow your own. You grow your own.
you are
plants.
fully living. You're living
Yeah, that's
really
crazy.
committed to this.
Yeah, well, it's the reason why I wanted to do this topic.
Yeah, that's cool, yeah.
That's a great example of bringing something that you're really passionate about into your work. Well done. That's really Danielle. Just bear in mind you're still sharing your screen.
Yeah.
Oh. All the things at the road then. On your book. And I might just make sure that where Danielle stands is a reasonable angle.
I'm a bit short.
I'll tell you when she's there.
Can you see me on the screen now? Is it okay?
Don't move anywhere halfway.
I move a lot, so what competition?
Move across the
Yeah.
okay, go.
Hi, so my name is Danielle, and my research project is Sign by Sign, which is done in collaboration with Cox. So imagine. Hello. Is it
Can you
okay?
come to this side?
Does it
Yeah.
work better?
Yeah.
Yeah? Okay, so so imagine going into a building, trying to navigate to your destination, but there was no signage to tell you where to go. As Huang puts it, it'd be as confusing as a maze. This induces anxiety, creates anger, and leads to a waste of time in critical situations. This spatial issue of wayfinding is encountered daily when navigating through an environment. So Lynch, an urban planner and author, defines the process of wayfinding as a consistent use and organization of definite sensory cues from the external environment, or simply put, how we get from point A to B. Signage is proven to be the most crucial to this, as it has high visual saliency and helps ensure people can navigate through unfamiliar environments successfully. Understanding how signage is placed is reliant on knowledge of how the space is put together, as well as how people move throughout it. This network of interconnection and interaction between spaces can be explained quantifiably through graph theory, which is a study of topological relations. While graph theory has been around for decades, its integration with architecture, and specifically wayfinding, is a recent endeavor. As the architecture, engineering, and construction industry slowly digitally transforms its processes and practices, So this is the way designers collaborate with the computer-aided design tools for automating design tasks. So my research looks at answering how graph theory can be applied to automate signage placement in the wayfinding strategy of indoor places. But before I answer this question, first we must look at why am I even bothering in the first place? Signage is nothing new. However, the strategies that we are using them to place them with indoor spaces are lacking. Current approaches to the design of signage and wayfinding systems involves a manual creation relying on experience and intuition of the designer. This approach is time-consuming and the effectiveness can be compromised through assumption. The layout must also be developed before any testing can be carried out on its effectiveness, which is typically later in the design process through VR testing or post-construction user testing. Along with this, the few studies relating to computational wayfinding theories and approaches tends to be on the urban environment. So my project looks at improving these methods through a data-driven autonomous design, which provides quick iterative analysis for any shape and design of building, regardless of how complex it is. The method also allows testing to be completed in the early stage of design, and with the lack of navigational support within indoor spaces, I've chosen that instead of urban space. So through these processes, aims of saving time, cutting costs, and creating data-supported decisions can be aimed to be achieved. Along with this, the project's objectives involves an understanding of how signage is optimally placed through spatial decisions. In order to achieve these objectives, a workflow of the process was developed, which outlines the steps that were undertaken to complete the project. This involves 5 main components of collecting the data, creating the graph, analyzing those results, and then visualizing them. So the first step was the collecting of data, which involves 2 main sources, Revit and Excel. The Revit model data includes the geometry of the floor plan, as well as the environment that the information that it's attached to. The Revit data is capable of being extracted using Rhino Inside, which is able to run a live Rhino environment within Revit. This allows for a connected workflow in which changes can be made and automatically updated and integrated. I'll put it on this side. Sorry. All right. So the points of interest are extracted using an Excel spreadsheet, which is fed into the script and extracted using the listed families. This did cause issues as families were inconsistently named throughout the projects. So the actual Revit family name had to be inputted. The Excel data used for this research is a sample file at the moment, but I'm hoping it will evolve into different files for different environments based on user journeys, so different for shopping centers or train stations. In order to test the system, a 2D Rhino environment was initially used. So the first step was to create a simplified version of the environment using surfaces which represent obstacles. To get a sense of how people would move through space, all possible paths that one could take were extracted through using a medial axis. Start and destination points could then be plotted throughout the space, which defines how people would move throughout it. By finding the shortest walk along these paths generated from start to destination, the shortest route that people would take most efficiently can be determined. Using these paths, the points that the navigational decision would have to be made can be identified. These points become areas for potential signage. Using these nodes as a starting point for decision making, the travel from the node to the destination allows a direction to be associated with each node. To reduce the complexity of the information provided, all angles were rounded into 4 main directions. Once the initial system was set up, several analyses was run in order to determine the necessity of the sign or whether additional signage would need to be added. This involved calculating the number of decisions made at each node and the corresponding weighting, which dictates the importance of decisions at that point. Which, as you can see, if I change the usage of the destination at the top from 80% to 30%, the surrounding nodes are greatly affected. The final set of analysis was the vision of each sign with consideration of the surrounding environment. This helps indicate areas of blind spots where additional signage may be needed, as well as areas where signage is most effective and reach the most number of people. So while signage is crucial, it's important that only the important information is relayed. Even if the environment is not very complex and has good visibility, if there's too many signs, it can lead to unnecessary confusion, which can lead to navigation errors. Likewise, if there's minimal signs which are not within a visible range, reassurance signage may be needed to be included. This can be facilitated by having a min and max viewing range, which alters the numbering and positioning of nodes to be within a set range. So initially when doing this, the nodes were placed within random corridors or with no vision or like no places where people don't really go. So in order to ensure that the new nodes were placed in non-inconvenient locations, the new positioning was weighted based on the prior analysis of visibility and centrality of the nodes. After iterating through the possible situations, a result is generated with statistics attached. So these values are able to change with adjustments to layout or change in start-destination pairs. Information on the visual analysis of the new layout can also be toggled on and off. This includes density, weighting, and visibility. While the fundamental of the code remains the same when transferring to a Revit environment, it is much more complex than that simple Rhino environment. It also allows for the boundary geometry and points of interest data to be automatically generated from the data inputs, removing the manual process. So because of this, several floor plans were tested on to ensure the flexibility of the script to different spaces. So first was a building that anyone who's used Revit probably remembers, which is the Sample Advanced project. So the script was able to successfully manipulate to the new environment. And because of the new information provided, I put in an Excel table that provides the scheduling for the information. The next model tested on was a Cox project for Ausgrid. The project was divided into 3 main buildings, so an engineering and commercial office, a logistics warehouse and workshops, and a retail cafe. So due to the short amount of time, I decided to focus on the most interesting and complex building for wayfinding, which I found to be the office. Just like the first project, it was able to adjust. However, the reliability became an area for question. Because of this, I decided to use one final project, which already had a signage layout placed within it, in order to compare and evaluate. This was another Cox model of a metro station. After completing the same steps as prior plans, as shown, we were then able to compare this result to the existing signing location strategy. And it's clear to see that the resulting areas of decision-making are quite similar. However, the spacing and splitting of signs is not made as clear in the script, and it shows that the research still has room for development. So while the project has many successes, it also falls short in some respects. The flexibility and accuracy of the script is reliant on an accessible database of points of interest and user group that must be created for each environment. There's also room for further development in terms of looking at user groups and accessible route information, which can be integrated into the decision-making process. The outcomes could also be further assessed and refined through the implementation of agent-based simulations or virtual reality testing. While the script worked well in modifying to new environments, the result does not locate the exact position of each individual sign extremely accurately, nor does it determine its specific sign type or graphics. Instead, it serves as an assistive tool through identifying areas of decision-making and what decisions are made there. This can help advise information that is required on signage in certain areas. So with further time and resources, the research has the potential to extend by potentially serving as a system for advising digital signage display, so feeding it through real-time data. So this is able to detect current uses within an environment and then able to change the information at certain locations in order to reduce clustering and help guide users for certain events. And overall, our understanding of the complex behavior of space and movement is the first step to improving the design of our spatial automated systems. Thank you for listening.
That was really interesting. There's through the whole process some slight changes in the actual way that
Yeah.
I think you ended up in a really good way with the direction of the vectors. It actually beats the Rhino way, I think, substantially. Where you can actually graph it with more detail now.
Yeah.
So well done.
Thank you.
Yeah, it's a really thorough and like it's, you've been diligent throughout the process and worked really with focus
Yes.
to did ask if there are any questions.
I can only see half of it. Do you want to read it out?
Was there any accommodation in the scripting to allow for stable users? Oh, hard question.
No, see, so as I said in the limitations, so having an accessible route is something that I haven't considered just yet. But as I said, it would be an opportunity for further development in the future, as well as other user groups.
Yeah.
So yeah.
So at the moment, the tool enables you to pick decision-making points where signage would ideally be placed.
Yeah.
But like it wouldn't. It's only in a 2D plan sense. It's not accommodating for height or.
No, not high.
It's
No.
not telling you any of those kind of.
No, not yet. So yeah, the specific details of like the height, the graphics, that kind of stuff, isn't like it's not included just yet. No.
So sorry, you probably covered this.
That's fine.
What do you think the tool as it is, I guess a quantitative tool, really, like a mathematical tool. What do you think it can't account for in terms of?
So yeah, the one thing that it doesn't really account for in terms of like human behavior is like navigation errors. So not everyone will follow, the shortest path to get to somewhere. People can make a wrong turn, things like that, which is where I think agent-based simulation would be good to refine the whole system.
Yeah, exactly.
Yeah.
Actual behavior.
Yeah.
Because I think one of the, in wayfinding, one of the other things, and I have actually read your thesis, I won't add easy, I keep saying easy. But I have actually read yours, and I think there was a question in my mind, and you may have actually mentioned it, but yeah, one of the challenges with signage placement and wayfinding is being distracted in the environment. So while someone might see a sign, then they might also like trip over something on the ground, or someone might run past them. Or so there's that, and I think that's where the agent-based simulation help pick that up, I guess. Because as much as we can, and this is one of the limitations of really, like you look at a plan or a 3D model and you think that's the ideal placement, but until you've got a crowd in an environment and you're like me, like 5 foot tall, and you can't see over someone's head, and this is I'm not in a disability class. People in a wheelchair have 1,200, height, eye level. The average eye level is 1440. I'm only 1500. I'm not meeting any of those average targets. But and so when you start to take into account the complexity of a crowd and the different users, and then trying to, it's always that how do you meet a little bit different needs?
Yeah. Humans are complex.
And this is like way up. Well, we can put it here, but we might, sense behavior thing that's super interesting. And obviously, there's been a lot of modeling, agent-based behavior modeling that's used for sort of fire scenarios, like how people exit buildings and transport environments and pedestrian modeling. Michael had a question for you. Can you see that one?
No.
Do you see other opportunities? Do you see opportunities for other applications? He also said nice presentation.
Thank you. So yeah, as I said, I think it'd be good to have as like if there's like because a lot of signage is like has digital can be digitally made. So if you're able to determine like what kind of decisions people are making like on the spot and giving the information that people need at that time, it makes it a bit more dynamic. I feel like that's a good like future trajectory.
Because we treat everything, all the signage here is
very static.
But once you can real-time data, change it up,
Yes.
Fantastic.
Okay. Thank you.
Oh, I did go out and come back in. So maybe that's. Oh yeah, yeah.
Yeah.
Yeah. Awesome.
Okay. Is it? Oh.
I think that's introduced. Oh, we'll start. Right?
No, it's.
Get the whole juice.
I don't know if it works. Oh, sorry. Wait, how do I do the full screen? Where is it? There.
Yeah.
Yeah, you look good. You have to say you look there.
I don't know. Okay. Yeah. Okay, so for my research project, I looked at how wind can sort of affect the design of an apartment building geometry, and I worked with Rick from Krone Architects. Okay, so the research background. So the research project is driven by the need to work in harmony with wind conditions in the urban environment. So after the 2003 Hong Kong SARS pandemic, it was found that the disease spread quickly due to the close proximity of windows of apartments facing each other in a confined airwell. And therefore, it was also found for a need to better understand the urban wind environment in high density cities. And the 2020 COVID pandemic has also brought light to the need of understanding airflow movement again for dispersing the disease, as well as bringing fresh air to ventilate homes. And so in order to understand the wind movement computationally, CFD was used through Butterfly, a Grasshopper plugin, and this allowed for the calculations of wind movements, which we can then visualize. CFD calculations takes time and can be slow, as it is a complex calculation. The geometry optimization with wind is not as common as with solar or light, and therefore it was challenging to grasp the optimization objectives against the results given by the CFD analysis. So the research question for this project is, how can a design workflow incorporate the wind data and generate apartment building geometry options to satisfy both pedestrian wind comfort? And through this, the objective was to create a workflow that, one, analyzes the wind condition in the envelope, generates a building geometry, and three, the building geometry needs to aim to satisfy pedestrian wind comfort as well as allow appropriate airflow through the urban environment. So this is the result of the research project. So it's a workflow that sets up the geometry, analyzes wind conditions, builds a new geometry from the results, and analyzes the wind conditions for the new geometry. So in part one, the envelope of the site was located, isolated, and simplified, and a wind rose analysis was undertaken to see the wind strength of every direction. And so due to the 10-week time limit of the project, together with my industry partner, we decided to look at the strongest wind directions, which was the west and the south. So next is the analysis, and the analysis was conducted with horizontal planes with the winds coming from the west and the vertical planes the south. This process took a good week and a bit to finish. As explained before, the CFD calculations and meshing took a long time to complete, and each calculations took a good 3 to 4 hours to be done. The results are then placed in separate containers and internalized as a way to save them, as the results will be wiped once you close Grasshopper. So it's not that great. So this section of the workflow, which is the geometry generation using the data from the first analysis, was the most challenging. And I had originally wanted to use an optimization component to generate the building geometry that would satisfy the pedestrian comfort levels as well as allow for adequate wind ventilation in the urban landscape. I had gone through variations of scripting for this process, but in the end we had to scrap it since the logic behind the scripting wasn't really working out. And so in the end, with my industry partner, the best possible solution for this was to use the resulting points of the initial analysis. And those points within those geometries, as seen by the spheres for visualization in the last image in the top, was to move each of these spheres to the corresponding average vectors. This then creates a surface which is then extruded and fitted within the focus building envelope. So these and the surface changed depending on how far the points moved, and the movement ranges between 0.0 and 1.0. And the final results I picked out was 0.2, 0.4, 0.6, and 0.8, and they're all fitted within the perimeter of the original geometry. And so another final analysis was undertaken at these 3 levels, with only winds coming from the west. And these are the results. The first column is the analysis with the original geometry. So this is what is used as a reference to see what has changed. And then straight away we can see that as a whole that the wind speeds are different at each level of the variations, which makes sense. And the strongest winds happen at the canopy layer, which and the wind is weaker at the pedestrian and podium levels. So the new geometries are no longer completely flat, they're curved, and some have more mass at the bottom and some at the top, and they are just essentially irregular surfaces. And this is one difference that we found. So in the original geometry within the circle area, there's a congestion of wind traveling from the west, and it sort of moves up, and that sort of creates like a really strong wind tunnel. And however, in geometry 0.2, there was a cutout in the bottom, which is kind of hard to see, but essentially it sort of dissipates that wind tunnel, and so that you don't have that strong wind moving upwards. However, we can see that the curve on the bottom actually creates a path for the wind to enter from the top. But 0.2 geometry was the only one that showed this result, and the rest was much like 0.4. When looking at the results, I also referenced Lawson's wind criteria. I have the new geometry and the original geometry average wind speed results in the table, and we can see they are not in the unsafe levels of winds according to Lawson's wind criteria. But we must also keep in mind that these results only look at wind coming from the west, and it'll be more than likely different if we look at other wind directions. So the research at this stage proved to be more of an analysis tool instead of to visualize and understand the wind movements in the urban environment, instead of a tool that somewhat solves a problem. So to recap the objective in this project, I created a workflow that analyzes the outdoor wind, creates geometry from the results in the initial analysis, and finally analyzes the new geometry to see the changes of the wind behavior. To determine whether the change is good or bad in that it satisfies the pedestrian comfort levels is something that the user has to look at and determine through comparing results. So the biggest challenge in doing this project is really the time given, especially with wind analysis. The time it takes for the calculation to be complete is a lot, and there are ways to lessen the calculation's time. However, there's a risk of not getting a complete result, and there's a difference that you can see. So one, we can limit the grid size, which dictates the amount of points and vectors the calculations will have. And if you have a large number, the less points, and the results will look sparse, and smaller numbers will result in more points and more to calculate. So it's important to find the right grid size and end time so that the calculations doesn't take too long and it doesn't look incomplete. And another limitation is that the workflow can only take one wind direction at a time. Future steps. So firstly, for this project, with more time, the workflow must analyze with other wind directions to achieve a more cohesive results. And further developments on the workflow could account for fixed variables such as trees or fixed objects that would mostly affect the pedestrian level. And another possible extended work is looking at indoor wind analysis for window placements or layouts to ensure cross ventilation. And another element that could be looked at would be really exciting is multi-objective optimization. And this could account for solar, wind, or views of an apartment geometry and generate the best geometry that balances the best options. That's it. Thank you.
This operates as an integrated tool, for modeling and analyzing.
Yeah. Yeah.
So it's interesting that you came to the conclusion that it operates more as an analysis tool than a design consulting tool.
Well, at this stage, with what I've got, it's more of an analysis, or it resulted in a more analysis tool. I had wanted it to get to a stage where it's more of a, well, it solves a problem, like it reaches an optimization stage. But yeah, we talked with Rick, and like it just wasn't working, and so this was the idea he actually gave. Like this was what made sense to him, and so, and you know, this is how it worked out.
Yeah, so I was just wondering, even with the analysis component of it, you're generating 3D geometry, which have beautiful sort of undulated form to them that could, in and of itself, be inspiration to think about a way to design the building. So I think that the information that's being generated spatially, formally, through the tool, I think is quite valuable in and of itself. I can see how you know, as a designer, that's the information that you want, and you are the designer, right? Like a lot of a design role is judgment, looking at different options, gathering data, and then bringing it together and trying to figure out what the priorities are in design. And multi-object optimization is trying to do that, but there's just a lot of hurdles. Like
Yeah.
You know, it's proving it's a very, I think Brady used the word holy grail before talking about integrated software, but I think multi-object optimization is like the holy grail kind of thing as well. Like it's something everybody wants, but it's quite complex to resolve. And I think, you know, this is a great first step, but I think even without that, it's just those. Yeah, I was just really interested to see those forms that were being generated. And I can imagine that even at a really simple level, if you sort of come onto a site and say, okay, the prevailing wind darkness in the west, and you run that optimize to the west.
There's always going to be wind from other directions as well. Though.
Yeah.
And so
That's right. So you do need, the tool we've got to account for all of it.
Yeah.
I'm really excited.
No, I think it's really difficult for something very difficult to get data for. I mean, you know, because every day of the year it's different.
So, and the current CFD stuff is outside. Like you're exporting a model to a CFD software.
No, it's all within Grasshopper.
Right?
Yeah. Oh yeah, the others. Yeah. They bring it in to it.
Thank you so much. Oh my God, Alan's got a question. I can hear you.
Oh.
Do we read it for you?
I can't see everything, and it sort of cuts out.
He says that he agrees with me. Let's leave it at that. No, I'm kidding.
What?
He said a lot of urban design process involves collecting data like you have in your project, and the solution will then come from collaboration between people and site context priorities. Oh, that was my question. Yeah. Okay. Great. All right. Thank you. You can tell the virtual audience that we will be taking a short break. We've got 15 minutes. We do. Yeah, there's like 15 people.
Hey everyone. Sorry about that. We're just going to take a 15-minute break, Nicole, or?
Yeah, perhaps 20.
20-minute break. We're gonna take a quick 20-minute break, and then we'll reconvene back here at around 12:35. Yeah. Okay. Yeah. So we'll start again at 12:35. And for those that are presenting online, please make sure that you're in the session 10 minutes before so I can give you sharing access. And then that's for the other session as well. If they're in the, or if you wanted to look at this chat, just make sure you're in your session 10 minutes before so I can give you sharing access. But all right, I will see everyone back here in 20 minutes.